Welcome back to Networking Basics. This is part 2 of network media and interface cards. And in the previous lecture, we stopped with talking about routers. And I need to mention that with each type of connectivity device, whether it is a hub, a router, a switch, or a router, you either have more bandwidth or you have less bandwidth or you have more efficient traffic delivery or you have, say, less efficient traffic delivery, less congestion, more congestion. So you're really giving up something and gaining something with each type of device. And when you're in network administration, you have to be aware of the fact that this is what is happening, and you'll certainly have to be aware of that. The router, as I mentioned, is a connectivity device that can connect two or more network segments, and these are called subnets as well, and they send packets to their appropriate destination and can thus be used to reduce network traffic in each segment. Also, routers will not forward broadcast as well, so that will reduce congestion in your network. The thing to remember about a router, though, is that it works at the network layer of the OSI model. So rather than dealing with the physical MAC addresses of each machine, it uses the logical network addresses, the IP addresses or the IPX address. And unlike bridges, routers can connect networks using different architectures such as Ethernet and token ring. There are two kinds of routers basically. There is the static router that uses a fixed routing table entered by administrative personnel, and the dynamic router, which will maintain the routing table intelligently, so to speak. Multiple dynamic routers can use routing protocols to notify each other of routing table changes and thus keep the routing tables up to date. I mentioned also that there are routing protocols that dynamic routers use, and two of them to mention right up front is RIP, which is known as RIP. You have RIP version 1 and RIP version 2, and OSPF, which is Open Shortest Path First. RIP can be used with TCP/IP and IPX over SPX networks. This is a distance vector routing protocol. Its routing table lists the number of hops or nodes the packet must be forwarded through for each destination, and packets are sent by the route that requires the least number of hops, so it's the shortest path. OSPF, though, which is a open source routing protocol, and it's used with TCP/IP networks, is called a link state routing protocol. It's the main improvement over RIP is that while RIP, RIP routers frequently retransmit their routing table, adding traffic to the network, causing more congestion, OSPF routers only broadcast notices of changes to the routing table. So it kind of reduces the congestion there. It's also open source. It's not a proprietary routing protocol. Hubs, repeaters, and bridges are usually hardware devices, but routers can be, instead of being an actual physical device, can be a piece of software that's running on a computer. Windows NT computers with multiple network cards can actually act as a static or dynamic router. Routers are more sophisticated than bridges and work better for very large scale networks. Their disadvantages, of course, are their higher cost, and the less available bandwidth due to the messages used by the routing protocols to maintain proper routing. Most modern routers add a negligible amount of delay to network transmissions. Routers only work with certain network protocols called routable protocols, and the common ones, the ones that you hear about, are IPX, TCP/IP, and AppleTalk. The old Microsoft NetBEUI protocol, often used with Windows NT systems going all the way back to Windows 95, is a non-routable protocol. So a bridge is a better choice when you use Microsoft NetBEUI segments. Then there's something called a router. The router is a hybrid-like device that combines the functions of a router and a bridge. If the packet is sent in a non-routable protocol, it is routed or filtered based on its MAC address. This is an extra feature that a router doesn't actually have, a pure router. Many of the hardware routers available today include a bridging function and thus are actually routers because they combine the functionality of the regular router that can filter based on IP addresses and IPX addresses. And the bridge can filter based on MAC addresses. Routers operate at both the network and the data link layers of the OSI model. They are most useful when both routable and non-routable protocols are in use on the same network. And the next idea we have is something called a gateway. And a gateway is another type of device that can connect network segments. And this is a very special type of thing because it's used to translate between protocols and data formats. Gateways can connect vastly different networks. For example, a common type of gateway will connect PC networks with mainframe networks using the SNA architecture. A gateway can perform a single translation or several, and translations are important because you can have different types of networks. So one type of gateway might connect a PC LAN to, say, a Unix network and translate a number of protocols at the same time. A more specialized gateway might be used to translate between different email systems. This is another example, such as Microsoft Exchange and the use of SMTP, which is an application protocol in the layer at the top of the OSI model. Depending on their particular functions, gateways operate at the layers of the OSI model, ranging from the application layer to the transport layer. Gateways are usually software services running on computers rather than dedicated hardware devices. Gateways provide functionality beyond that of a router in translating between networks and should only be used when these features are necessary for running your network. Ethernet, as you know, is the most common network architecture worldwide in use today. It was developed by Xerox, Intel, and DEC in the late 60s, and it was revised as Ethernet 2.0 in 1982. Ethernet networks use the CSMA/CD media access method. That stands for Carrier Sense Multiple Access with Collision Detection. And that's defined in 802.3 under the IEEE. These are three 10 megabit per second Ethernet standards for different media types. And you know these already. There's 10 base T, which is unshielded twisted pair, 10 base 2, which is thin net or thin coaxial cable, and 10 base 5, which is thick net or thick coaxial cable. As you can imagine, each one of these standards has its limitation. And for example, with 10 base T, you can have a maximum of 1,024 segments and a maximum of 1,024 nodes when using that cable standard. You can also have a maximum of 4 hubs, and you can have a maximum segment of 1. The distance, the segment length that you can go is 100 meters. There's that magic number where the signals can begin to retard on a lot of this cable. And you keep that number in mind. It's only 185 meters with 10 base 2, and then it's up to 500 meters with 10 base 5. So when you look at the reading material, you'll see some charts and graphics in there that help you to gather some information about how this all comes together. 10 base T is currently the most popular Ethernet implementation. 10 base T Ethernet uses unshielded twisted pair, which there's no shielding there for EMI, and it's in category 3 or category 5 cable. The system uses what is known as the physical star topology with a central hub, but the hub's internal wiring will form a logical bus topology. 10 base T supports active and intelligent hubs. 10 base T networks are easy to install because UTP is easy to handle. They are relatively inexpensive too, and easy to troubleshoot, and you can have diagnostic capabilities of active intelligent hubs to help you do that. In the real world, 10 base T standard does not actually specify a distance limitation. The widely known 100 meter limitation is based on the limitation of UTP cable. So it's definitely something that's in consideration with all of your administrative concerns and questions. 10 base 2 is thin net. It uses thin coaxial cable in a bus topology. And you'll notice that it uses the RG58 military spec shielded cable. There's a third type, is RG58U, uses a solid rather than stranded core. These are a little bit more detailed than you probably need to know, but this type of cable may work, but does not meet the IEEE specification and will be unreliable. Continuous cable is wired to form the bus. Sections of cable are connected with BNC connectors to a BNC barrel connector to extend the segment, or a BNC T connector to attach a node. Both ends of the bus are terminated with BNC terminators. At least one of the terminators in each segment should be connected to electrical ground. Thin net is seldom used, though, in large wiring projects today. Then there are 10 base 5. 10 base 5 is also known as thick Ethernet or thick net, and it uses an RG-8 cable. This is a thicker and more expensive type of cable. Thick net is rarely used, though, in current networks, and it does have some advantages, though, over thin net. It supports a greater maximum segment length of 500 meters and more nodes per segment. For this reason, thick net is sometimes used as a backbone to interconnect thin net segments. That's a lot to say. And due to the thickness of the cable, thick net cable uses taps that pierce the bus rather than connectors that require cutting the cable. Thick net follows the same 5-4-3 rule as thin net, but allows up to 100 nodes per segment, providing for a total of 300 nodes per network. Finally, we have fast Ethernet, and this is also known as 100 base T. It's a new standard for 100 megabits per second Ethernet. Fast Ethernet can use 2-pair category 5 cable or 4-pair category 3 through 5 cable. 100 base T uses a physical star topology identical to that of 10 base T, but requires that all equipment, hubs, NICs, and repeaters support 100 megabits per second speeds. Some NICs and hubs can support both standards, but all devices on the network need to be configured to use the same standard. So we have a fast Ethernet, and under that we have something called token ring too. Token ring architecture is defined in IEEE 802.5. IBM created this, and it's further defined the standard to include particular types of devices and cable. Token ring uses a logical ring topology and a physical star topology. The hubs used for token ring are called multi-station access units, or MAUs. The token ring standard supports either 4 megabits per second or 16 megabits per second speeds. And cable can be STP, UTP, or fiber with token ring. One popular wiring scheme uses Category 5 cable, and there are also a variety of cable types defined by IBM. Well, there you have pretty much our conversation ends on this different network media types. Just keep in mind that as you study this material, you're learning different implementations and different physical layouts that you will find probably in many different businesses. There's often a mix of these. There's not just one predominant one. A lot of data centers, for example, large ones will have implementations of different standards and different topologies, and it'll all be for different kinds of purposes and different kinds of support. I hope this has helped you to get some grasp of network media and the interface cards and how they come together. Thanks for listening, and we'll talk to you again soon.